that way. It's like, there's another way to do it.
Yeah.
But it's not really not large, so I'm not sure why.
So, why don't you just extrude it, make one side first and then just mirror it onto the side after. Like, don't do it in the sketch. Yeah. I don't know why it's on a smooth, not all the work. Oh, yeah, like that doesn't show up. Yeah, that's what I'm thinking. But it doesn't matter. So
You just have mirror.
yeah.
Oh,
Yeah, mirror we can just because it's sketch. You don't, yeah, it's just get. So why don't you try it? Just get right? You want to mirror the solid.
EGY 12.
That's another way to do it. That way, normally when we do mirror pattern, you want to
Alright, so welcome back everyone. So now we're going to be doing a bit more about 3D printing itself. Some of this stuff was covered by the induction at design build. But we're going to put more exercise now talking about, what in terms of what we're thinking about in the model 3D printing. Yeah, so in terms of materials, one of the things I forgot to mention in the pre-check is always check that the material that you're printing with is the material that you need. Because each material will have different temperatures and stuff like that. But the one that basically all the proofs will use first up would be PLA or polylactic acid. So here's a lot of info, but basically PLA is used for all the prototyping. It's easy to print, it's hard, but it has low flexibility, okay? It is odorless. Okay, and it can print large designs and it can print really small designs as well. And the reason why we use it so much is because it's really affordable. Okay, the disadvantages is it's really brittle. Okay, just because it's so hard, it snaps really easily. Okay, and has a low temperature resistance. So that basically means that anything above 60 degrees, it starts bending. It can bend as well. That's why we keep that build plate temperature at 50 to 70 degrees. Okay, the other bad downside is that it's UV degradable. So it's polylactic acid, so that means it's organic compound, so UV will break it down quite quickly. Well, not too quickly, but it's a decent amount. You lose strength over time. The next one is ABS. ABS is not used too much nowadays because we use another one, which I'll talk about called PETG, but it has really high impact and wear resistance. It can tolerate really high temperatures, okay, and it's UV stable. And the really good thing about ABS is that it's soluble in acetone. So what that means is it completely melts away in acetone. Okay, so we use it to glue things together, and we can use it to smooth the surface of our print as well. Okay, so disadvantages is that one, it's difficult to print with. Okay, so it needs a really fine print settings to make it sure it's correct. Okay, it has a real tendency to warp as well, just because it has these strings. And then the really main one is that it has a really bad unpleasant odor. If you ever print with it, you'll smell it immediately. Okay, and then with the extruded temperature, we need that higher temperatures for it. So 245, 265. On the build plate, it's 90 to 110 to achieve a good adhesion. So the next one that we have is PETG. So if you guys remember on the Prusa printers, you see those parts, orange parts that were printed. Prusa has a lot of printed parts that they make from, and they use PETG for those. So they use this. Okay, so PETG is basically like PLA but better. Okay, so it's more ductile and stronger. Okay, has good temperature resistance. It's still odorless. Okay, but it has really strong layer adhesion. Okay, so that gives it that water and humidity resistance. Okay, so it's used a lot in commercial applications for when we've done prototyping. The disadvantages are that it's UV unstable. No, that's an advantage. It's UV stable. It has better UV stability than PETG, than PLA. Okay, but due to its really strong temperature, high temperature, it prints at 240, we get something called stringing and bridge. Okay, so that means that if you have two towers, for example, it will accidentally form band between the two. Okay, that's because of the high temperature and it's really strong adhesion. Okay, and it's quite hard to remove. That's the other thing, just because of that high. at heat as well. So with the extrude temperature, that's at 240 degrees, and the build plate temperature is 80. Okay, the next one that is good is TPU, or thermoplastic polyurethane. Okay, so this is our flexible one. Okay, so it's soft and stretchy. Okay, we use for anything that flexes, or we want anything to flex. So it's shock and vibration resistant, and it's also chemical resistant. Okay, and it has a low thermal expansion. So when we think about thermal expansion, we think about if it's going to contract after we printed it. Okay, so the disadvantage of this one, okay, is that it's difficult to print with. It has a very fine control of the settings. Okay, so each TPU filament will be different, and then you have to find control, and you have to print many times. You have to print many iterations to make sure that your print is good. Okay, and the other thing is that it tends to clog as well. So it tends to clog that hot end, and it can string as well. Okay, and we have to print it at a really low speed to make sure that it's printing, and the layers are adhering to each other. Okay, the other thing is it's difficult to post-process. Okay, because you can't really sand it. Okay, because it's all flexible and stuff. Okay, and you can't really like deburr it or anything like that to get rid of the edge. Okay, and those are the temperatures: 220 to 230, and then build plate is 30 to 60. So for example one, this is something similar to what I worked on over the summer. So it's a bladder scanner. Okay, so what this is going to do is it's going to sit on the bladder, okay, or on top of the stomach, sorry, and it's going to use ultrasound to measure the bladder volume of pediatric patients. Okay, this is used to diagnose lower urinary tract dysfunction, and it's trying to replace, what we're trying to do is try and design this to replace a way more invasive method called system metrography, which basically they put catheters and all into your urethra and into your rectum just to measure it, and then pump saline into it to fill it up. So for this example, what materials would we use for different parts? Yep, okay, PETG for the waterproof casing, perfect. Okay, so we want that hard shell. Okay, and what about that bit that needs to conform to the stomach?
So the TPU.
The TPU, the flexible one, yeah. Okay, so we want that so it can sit on the stomach and adhere to it better. Okay, what about this example? We want multiple parts and we don't want visible lines. Yeah, the one that's soluble in acetone, so ABS. Yeah, so ABS. So we want those lines to be visible. And so there's something you can do with acetone, which is like you put it into an acetone vapor bath, basically, and that just the vapors smooth it all out. Okay, so the next thing I'm going to talk about is modeling for 3D printing. So what type of thought process do we have to use when we're designing Infusion to bring into Cura so that the print comes out nice? Okay, so the first big one that we have to think about is overhang. I guess this is with all 3D printing, but overhang. So when we want designing, we want to minimize the supports that we use. Okay, it creates a clean result, and then with less supports, we don't have to do as much post-processing. And if we remember from that Lego brick you guys printed, okay, the supports, you can't take them out, can you? They're really hard to take out, so we don't want that, okay? So that's why we have to reduce the amount of overhangs, okay? So the main rules are that 3D printers can't just print in midair, they have to build off something for it, okay, unless it's on the build plate, okay? We can't create complete overhangs, okay? We can create small ones, okay? But not very long ones, okay? And we have to keep the bridge length between 50 to 100. So what do I mean by the bridge? So if we remember like the two poles, okay, if we want to build a bridge between the two, okay, we have to keep that between 50 to 100 millimeters so then it doesn't sag. Okay? And then the next big one is that reducing steep curves, okay? We don't want anything greater than a 45-degree angle usually. Okay, and if it's unavoidable and we need to create an overhang, okay, we need to think about, we need to make access for the support material to be built to it. Okay, so for this example, I gave it away before, but okay, what's wrong here?
Longer to here.
Okay, yeah, that's a really big bridge, okay? So what's gonna happen when we print it? Gonna drop completely. Yep. Okay, and how will we fix it?
Support underneath.
Support underneath, okay. What else can we do? Choose the length, okay, but what if we need to keep that length? Yeah, what do you say? You can just rotate it. You can print it in a different direction. Okay? So instead of doing that, okay, we just print it flat. Next one. Okay, so when we're designing, right, which one do you think's better, fillet or chamfer?
Fillet is the one on the left, the chamfer is one on the right.
So hands up for fillet. Okay, and hands up for chamfer. Okay, so the people that put up their hands for fillet, do you want to tell me why? Or not?
It's not sharp. It's more smooth.
Okay, and then the ones for chamfer?
Same logic, but it's straight. So
The gradient doesn't like get too steep.
Yeah, okay. So yeah, because the chamfers are 45-degree angle. Perfect. So I feel it provides a smoother finish than a chamfer, but they must be printed in the XY plane, right? Okay, so if they're printed in the Z, it will create a really steep overhang. Okay, and then in the Z plane. And then we'll create a sag. Okay. Chamfers though are constant 45-degree angles. We like 45-degree angles because then we can print layer by layer on top of them. Okay, and it has good contact. So here's a little diagram. Okay, so here we see that, okay, we have good on the fillet, the chamfer, sorry, we have good constant contact with the previous layer. It's consistent. Okay, with that fillet though, okay, you see that first one to that second layer, there's a big gap or overhang, and then it gets more gradual after that. Okay, example number 5. This is YHD. This is a good little thing to test with your printer. We saw these yesterday. I think the demos went out. But what's going to happen here? Are we worried about the Y? No, yeah, okay, we shouldn't be because it's an all right angle. It's 45 degrees or less, right? What about the H? The bridge too long or is it enough?
Okay.
Yeah, it's a pretty short bridge, so we're not too worried about it. What about that T?
I'd say no.
Yeah, no. So yeah, that T will have that overhang, and if we have that, we give that the model.
Oh, yeah. Yeah. The one that's yeah, Yes. Yeah, so that'll just. It'll just print across there.
It will print across because
nothing is holding up to
there's
it.
enough, yeah, it's okay. 10,000 3 points for it to stay. Okay, so that's why we have that 150 to 100 millimeter. Anything longer than that, it's not doing that.
It's like a decent.
Yeah, you can do 10 centimeters, that's quite a decent amount, especially with the cruisers. Because they have that, you see on the side, they have that cooling fan. Yeah, so that cooling makes tools just.
Yes,
Sitting right.
before you put the next one.
Yeah.
It's the what? Like the first layer. Like, we did the jerk and. Oh.
Yeah, so.
Yeah, why?
Which example?
When I think about holidays.
Bridging in 3D printing is really
That's what it
Yeah,
looks
so
like.
See how it's, this is a bridge being formed, right? So in a Prusa, right, you see this bit here, that's a fan. You see that fan, that's a cooling fan that will cool the part, the print down. Okay, so that string can cool enough.
So it can go pretty far, but
You can go quite
it start. You can see it starts.
far.
Yeah, I'll show the final. Yeah, there you go. There's a difference.
So at 100 mils, it's not too bad. You can see some strength, right? So that's why 50 to 100.
Yeah, the bottom layer is still not as straight as it's supposed to be. So
But think about it as it's temperature versus speed, right?
Yeah.
Temperature and speed versus sag, okay? So you decrease the temperature of your build, right? It cools down quicker. You're not going to have that sagging, okay? Gravity's not going to affect it as much. You print slower, that also means that your filament can cool down as well and hold its shape. But at the same time, if you go too slow, then you won't connect it to the other side and you won't tension it.
cool.
Yeah, it's good.
Is it still connected?
Okay, so once again, with the YHT, how do we solve this issue? You can rotate it, yeah, or you can go with the floor, yeah, and which one we prefer?
Upside down.
Yeah, rotate it.
Yeah, like.
So then, yeah,
Yeah, do that.
either you can flip the T upside down, or you can build it flat, or you can put the H flat as well. Okay, so that brings us on to our next section, build orientation. Okay, so this is making our model at different orientations, either through Cura or in Fusion itself. Okay, why? Because we want to rotate the model to reduce overhangs. Okay, we want to think about the direction of the layers and how we want to optimize the strength of the layers. Okay, and we want to think about the direction of the layers to our set. Okay, because X and Y are very precise, but Z is that set layer height that we put it to. Okay, so this is an example here that I've designed. It's a tag holder for your tolling. Because I broke mine, so I just designed it. Okay, so what can we do here? Because obviously we have a massive overhang there. Yeah, rotate to which face? Yeah, so this one here. To make this one flat?
Yeah.
Yep. That's basically it. So yeah, we just want to print it that way, okay? Next one. Okay, so this is the example here, another example that I made. So I snapped the little thing between the doorknob, right? Okay, and so I just built it. Okay, so it does this, right? And then what happens is the doorknob turns either way. Okay. And then you have the forces and unlocks the door. Okay, which way would we want to print it?
Oh, this one.
The one on the left. And why?
Less overhang. Like on that one, you're sort of having the things stretch out quite a bit.
Okay.
The strength
Yeah, talk me through that. Okay.
So I think normally the Z-axis is weaker.
Mhm.
And so if the doors, so you're twisting it from outside to side. So if you have it that way, then you've got all your kind of fibers going that way, so you can twist all of them together. While with the other one, the strength is going to be between those layers in the direction of the axis that you're twisting.
Yeah. So this is this is where we weigh up. Okay, build orientation for easiness. Okay, so the one on the left will be way easier to print, right? Just straight up. Okay, but the one on the right is going to be harder. We might need a little bit. We might need supports. Okay, to help with that little overhang there. Okay, but if we print in the vertical direction, right, we're twisting it left to right, okay? This is actually happening, so I printed it vertically, okay? What happens, those layer heights are built like that, okay? And then they just snap, okay? Because the force is in the wrong direction. But if we were to print it horizontally, right? Those layer heights are like this, okay? So those forces are acting throughout the whole part, okay? So that's what we mean by when we think about strength, how we want to design our component, okay? The next example is this one, right? Okay, so this one is more for aesthetics. Which one would print better and look better? Yeah, why, maybe, but why would be the one?
It just looks like it has like, there's no point at which anything is supporting anything else. So like every layer is on top of another layer, whereas here on the right, you're building up 2 layers here, and then the layers at the very top are like have nothing supporting them in the very middle. So, yeah.
Okay, yeah, we can think about it in terms of support. Yeah, we'll have that sag as well. But think again, we have that infill to help out with that roof. Okay,
Just for the aesthetic, then with that one, you're gonna, each layer that it goes up, it's gonna be slightly off, and so it's going to create quite a rough surface.
Yeah.
Right.
exactly. So yeah, if we're thinking about layer height here, right? We have one layer. This X and Y plane, okay, is very precise. We can go 0.001, I think. Okay, this, we set the height, right? We set it to 0.16, 0.2, okay? So it's going to make 0.2 gaps every time, right? And so when we print it, I have an example here. Okay, we can see the difference. Not quite in those pictures, but have a look at these examples that are coming around.
Yeah.
Yes. Yes. Yeah, it is. Yeah. That one's on exactly the same.
Yeah, no, I've given up on this. It's like, it's like a couple of months off. It's- yeah. I'm
That
not
is
gonna-
really working
yeah.
on.
Well, at least fixing my-
Why did it use that?
But we will think about that.
I mean,
This phase.
oh, no, yeah, I'm trying this out. No,
No.
I think it's got so much oils and stuff. You can't see it.
Still one left. Just.
I was not. Let's see it. Let's see it.
No, yeah, it's like very dynamic. Yeah, it's so bright. I don't even know why.
So you have like-
Protected for it, but.
Curve or something.
It's just to look like you.
Like treatment of my computer.
Right?
It does.
We can find out.
Oh,
No, brother, don't do that. Don't do that. Don't do that.
Just right, even. Oh, yeah, I'm pretty sure that they had it swear I love the project, but I can't find it. Made an Illuminati lamp in object.
So which one's which? That one.
So much fun.
Yeah.
That's what we need to do.
Yeah.
Okay.
Let's take notes, take notes.
So you say that.
So the next thing I'm going to talk about is tolerance. We talk a lot about tolerance with CAD, but there's also a lot of tolerance when we think about printing as well. So we have to think about them differently. So tolerance when we're printing, okay, is the gap. Okay, so if we want things to fit together, we need a small gap. Okay, just because printer is not that precise. The printer itself is pretty precise, but the filament that comes out is spread sometimes and causes things to join together. Okay. So here are some just guidelines. Okay, if we want a very tight fit, 0.1 millimeters. Okay, if we want a tight fit, 0.15. Okay, if we want loose, 0.2. Okay, so here's, I guess, another little demo. For this part, right? So we have a gear, okay, that's connected to a shaft here in the middle. Okay, and then this is a bushing. Okay, this is a bushing that we want it to revolve within. Okay, so in this part, between the two parts, between the bushing and the shaft, what type of tolerance do we want? Yeah, a pretty tight tolerance. Yeah. So which one? 0.1 or 0.15? I'll go 0.15 here. Okay. So that's it there. You really wouldn't use the very tight tolerance just because the printer can't handle it. Okay. I don't really have any use cases. And I think you want to go to loose stop. So you want to go to 0.2 and above.
Yeah, we'll talk more about this on Thursday, but there's lots of different tolerances you need to understand, particularly when you're producing sort of industrial grade components. And there's also calculators that you need to learn how to use as well and how to calculate the tolerance accurately. Sometimes if you just manufacture the wrong piece, then it's going to be too loose or too tight and you can't fit it in.
You just intentionally designing like.
Yeah. But yeah, when I'm thinking about this, I want to make a decent, like a 0.1 gap rather than putting them right next to each other.
Is it normally like, you make this in a 0.075 small, the other one is a bit bigger, or is it one?
It depends which one, really. Like, it depends which one you want to be the actual true to shape one.
Yeah.
And then which one that you want to hit. Like which one you want. Yeah, it depends which one you want. Like, so for instance, right? For example, this bushing, right? I want it to fit a certain diameter.
Yeah.
So then I would fit the inside shaft to that bushing.
Yeah.
So it really depends, dependent on which one. Like it's the primary, yeah, the primary. Okay, so what about this example? It's coin sorter, okay? So you just put a coin in and it rolls down and then it sorts your coins. What type of tolerance do we want for that? Yeah, a very loose tolerance, okay? So they can fall into it, okay? So we can fall into it very easily. Okay, so on to our next thing. What would we do if we want to print a sphere? What would happen? What's that for?
You might just avoid them.
Yeah, so it'd be a bunch of supports, otherwise it would just completely collapse on itself, okay? Or it would sag quite a bit. So how would we solve that issue here? Other than supports? Yeah, so you can cut it in half, print two separate halves, and then join them together afterwards. Okay, so that's the whole point of multiple parts here. Okay, cut it in half, print the exact same thing twice, okay, and then join it together. Okay, so it's often better to split complex models into separate parts. Okay, so it creates more flat surfaces to start to build on. Okay, better adhesion. Okay, and it can create better, or will create better visual and mechanical properties of the part as well. Okay. Think about the support, right? When we build supports, they have to attach somewhere, and then we have to do a lot of processing, sanding stuff to make it smooth again. Okay, versus cut it in half. Okay, we have two flat surfaces that we can join together that no one's going to see, and which will make it a lot better. And then here is an example. So here's what would happen if we try to print it. Okay, that's the supports joining up to it, which looks kind of cool, but then on the right hand side, you got this in half, so much easier to do. Okay, what will we do for this example then? How we split it? Yeah, split into which three parts? Okay, could you do it in two? Could you do it in two?
You can do it in one, right?
You do it in
I
one,
thought-
though.
You can do it in one,
Yeah.
but like,
You can probably do it
Yeah,
in two.
exactly.
yeah, you can do it in one, but for this one,
Thank
you
you.
can do it in both.
Yeah, yes.
I'm digging a hole then.
Yeah, so then, yeah, you can split it into two parts here, right? So then you have to make a little connection between the two, otherwise they won't combine anymore, okay? But that's another example.
Yeah, the connection thing.
Okay, so now we're gonna go back into our Kura settings,
Oh,
talk about them.
you actually open it up or?
Yeah.
Oh,
And open up Fusion as well.
oh, man. Just a multi-window. Oh, yeah, that's one.
So we're gonna pass around sort of like three parts and you can see a little bit about tolerancing and like how we can make them fit into each other as well. So the bonus setting.
This is point and brick design.
Your one's better. Oh, this is another part, and you can see why I love creating this one as well. So I got it wrong.
Sometimes still there.
So this is why part the wrong. Why I put this, I broke it like this, and you can try to figure out why I did it wrong.
Yeah.
Why I need to
What could be?
Have you done your motion?
And the only thing I did here was that. 0.2, I think it was 0.2, yeah. And that's how it feels like, it was like 0.2, yeah. They're all 0.2, yeah, so there wasn't.
It must be better miles.
Something else.
First of all,
You can try to put your phone on it and then see how it stands up.
no, but Arnold.
You have the slide.
That's different though. You don't want to-
Yeah, exactly, yeah, exactly.
You're the.
And then
No,
No comprehension, nothing's happening up here.
try to switch it out. I could probably make it even better, if I just put another one, but like.
Yeah, exactly. You can make a typewriter.
Make a phone.
Okay, so I think everyone's already done this, but if you haven't, in Kura, can we go to that three little lines and then change it from whatever it was before to basic setting?
Whoa. Where's
Where
that?
are they?
Oh, it's not there?
Oh, yeah,
Yeah, basic.
no, mine's not up there.
Click show custom if it's not there.
Show button.
Click that show custom button.
Is-
Yeah. It's exactly.
Oh. It's already up, basically.
You want it to be blank, blank.
You know, they really good at that though.
Oh, of course it is. It would.
Painting, but there you
Yes,
go.
it is. I was wondering like, yeah. Definitely wasn't drinking.
You were drinking it.
I was drinking like food, watching a movie. Yeah.
Okay,
A little whiskey cola.
so now in back in Fusion, I want everyone to make a 50mm by 50mm image, and then just import it into Kura. Help us demonstrate the benefits.
Bravo, you're gonna.
Robert, that's gonna take me at least 2 hours.
Yeah, and whoever does it first, put their hand up.
Yeah, I mean.
I might.
And then teach you on.
Can you drive me there? Pretty please?
Then I have to remake it.
Cause they're gonna be.
Trying to figure out what page.
Before, wait, actually.
Wait,
Put
well,
one on
I
it.
mean, technically it's not that, but. Let me move.
Oh, yeah.
Oh, you live on red. Oh, Mannix,
Yeah,
you know David?
yeah, go on.
Hey, do you know who I am?
How should I know you?
Oh, great.
You are a hot shot. So you are.
No, I know a lot of people on Mannix.
Such as. One person.
Oh, nice.
Into Cura, into Cura.
I gotta import it, you gotta import it. Yeah, Kira's on there.
It's so scrap paper.
Yeah.
What's this?
No,
You must be thinking about it.
yeah, I think so much as we have to. Why is it just scrap paper? Hilarious.
You just let me get off my brain.
How do you export? Bottom is STL. Yeah.
Oh shit, I'm trying to make that one.
No idea.
Bro, how do I get a cube again? How the fuck do I get a cube?
Oh, wait.
Yeah, I'm asking. Did you like no, actually, I thought that effort productive.
Wait, there's a cube tool? Really?
You're playing.
Sorry, I'm
Yeah, you're gonna come to the party on Friday. Oh, are you? Damn, ew.
Yeah.
What's that cut though?
I think so.
Mine's in Queensland.
Isn't it easier to get your license in Queensland?
Yeah. What? I don't have a car.
Which one, Queensland?
I put it on my thing, bro. Queensland? Up to the road, bro. Up to the road. Oh,
Brisbane.
You?
2 hours Brisbane.
What?
2 hours west of Brisbane.
Where? Or up to
Yeah,
it's more, right?
Yeah.
Yeah, that's tough. So you came here for.
So shorter, bro, than Queensland.
Sort of, exactly. That's the reason.
That is JCU.
Alright. The boys from JCU is like, it's tough.
Yeah.
They're all on placement in year one still.
That's good, they're constantly on place.
Yeah, but like, they said like their first email was like how to be safe.
I don't know, well, I know a couple mates that are up there.
Their cars got like, the plates get full all the time.
Really?
Yeah. Like plates and canvas, bro, it's deadly. Just do that.
Okay, has everyone got that cube in Cura now?
No, I haven't shit. What would I do with it?
Right, and then make. Remember section here.
SDL, ACI, millimeter, refinement meeting. And we're not doing that.
I thought very differently.
Yes, let's get rid of that.
Oh, yeah, I've got it. Between me and
See, like, I'm just about that efficiency.
because you don't know keep a brown. Obviously, step.
Yeah. I was thinking, I am. But yeah.
Maybe.
Went to school. Okay.
Went to school in Brisbane?
Yes, sir.
What was school? I knew it. I can tell, bro, I can tell you. Which school am I from?
I don't know. Are you from Brisbane?
Yeah, Brisbane.
What's your
I can tell straight away.
Yeah.
They're hiding each other. You guys always are number one optinator. We always say that. So high gives somehow that all produces 99.95. It's corrupt, bro. The one only is good state high school. QE definitely does a confidence. He's an A type one.
Yeah, you're not wrong. Okay, so now that everyone's got that cubed in, we're gonna move into infill. So if everyone wants to open up those settings and go to infill.
We should go to recommend.
Okay, so for infill, we can split it up into different patterns, right? We can select the patterns. Okay, and we choose the infills based on their use case. Okay, so we can do it for standard prints, functional prints, and then flexible prints. Okay, that's our pre-made.
Oh, okay.
Okay. So you have a big list of these, so I'm going to break them down into which one's better for what.
Oh, should we do?
Okay. So for our standard prints, okay, so these are our basic models and quick prototypes, okay, that are subjected to low stress. We don't really care about putting them, compressing them, and then like throwing them about, okay, they're prototypes, okay, we just want to see if it works, okay. So this is grid, triangle, trihexagon, and a new one that I really haven't used called lightning. And lightning, I'll talk about it later, but it's pretty cool. Okay, so first of all, grid, okay. So if you want to just go through just while you have the cube, click it, slice it, look at the layout. Okay, and look at what it looks like. Okay. So grid is a basic 2D model, right? It'll do this whole format throughout the whole bottom to top of the whole
You
view.
choose grid as an infill and then you use the link bar. There's like a scroll bar.
To go to preview, yeah.
Yeah. Wait, wait. Yeah.
So 15, it just when you use it.
You're in
Oh, sweet.
Yeah. So grid, okay, is your quickest one. Okay, it's really quick because we've got straight lines across, okay? So the next one, triangles, is going to take a bit longer, okay, but it's going to provide more strength. Okay, so we want to do that, we'll look at it. These are all 2D ones, so you can go from top to bottom or just triangle.
Yeah, you figure out what.
Right, and then we have trihexagon, right? So that's that next one. It's hexagons with triangles on the side. Even more stronger, even more longer.
Oh, that's not.
I was gonna touch it, yeah.
Oh, that looks so cute. I put this every time more readily.
Okay, and then the last one we have is lightning. So lightning's a new one, okay, it's computer generated, okay? So it's an algorithm that basically calculates where it needs to put the things and where it's going to be strongest. So if we have a
Oh, what?
look, okay,
Oh,
if we have a look at what it does, okay, if we go through layer to layer, with the cube, right, it will only build it at the top. So it'll make a line, right, and then it does like lightning strikes, okay, in 3 dimensions, okay, just to support the top roof, to build that roof of the cube.
Which is better info. It remains the same.
Yeah. Yeah. So if we look, when you slice this cube, right, look at the time difference it takes, and the amount of material it takes as well. The lightning really is not really strong. Okay, it generates enough to support itself. Okay, so it's not really as strong compared to the other one we talked about. Yeah. Sort of. Okay, and so the next one that we have, okay, is functional prints, okay? So that's for models that need high strength in multiple directions, okay? We're thinking 3 dimensions now of strength, okay? And so a lot of these will look really weird, okay? So what I'm gonna ask you guys to do is go in the settings, go to shell, okay? Go into walls, top, bottom. Go into walls first. So in the settings. Go walls. Yep, and then set wall line count to 0. Alright. And then so the ones that we're going to go through is cubit, octet, water cubic, and gyroid, okay? And from top to bottom in this order, that's the weakest to the strongest one, okay? And as you guys are going around now, you can see that if you just click it, okay, so this is cubic, okay? And then you just go through the layers, you can see that it builds the infill in a 3-dimensional pattern, okay? I would suggest having a look at it at like a 45-degree angle. I don't know how to describe that. Like look at it through like this way.
Yeah.
Yeah, like that.
Oh, yeah, have to change the wall to 0.
Okay, the next one that we have is octet.
No, not thinking.
Right?
Yeah. Just set all things to zero so you can see the.
Okay, the next one is quarter cubic. So quarter cubic is the strongest one. However, it takes the longest amount of time usually. Okay, and it uses the most material. So we only really ever use this if we want a really strong cube.
Wow. That'd be good for my.
Okay, and the last one, gyroid, right? Okay, so that's a good balance between material, speed, and strength. Okay, so we want to do this one. We have three-dimensional strengths that we need. Okay, but we want it to be quick as well.
What's too long ago?
Really?
It's longer than I was. Yeah,
But no, mine took quite a lot.
yeah, Gary. It took longer for that.
Everyone gonna test
Yeah.
it?
Yeah. The whole hour.
Okay, so usually for the shooting.
Maybe the most.
This was the original part.
36 seconds, like, feels like
That's heavy.
oh, it's so heavy.
Mine's 40. Like, all it is,
Mine's 4.
Just drag that to a random.
Yeah.
Zoom in. Use that as well. And full screen, you're. Swear to God. See another application that's not full screen.
Okay, and then the last one we're going to talk about is flexible print. Okay, so when we think about flexible prints, we think about TPU, that filament that's flexible. Okay, so we want to keep the bendy nature of our build, right? So the first one that we have is concentric. Okay, so it builds these concentric rings straight vertically from the bottom of the cube to the top of the cube. Okay. Can someone, I guess, tell me which way would it be the weakest? Which direction would this be the weakest? Or the most squishy, I suppose. Sides. Which way? Would I squish it sideways or from the top?
One really switching back up to the top.
Yeah.
All the way up, or is it like rule?
I think it's.
Because you're pushing, like,
Yeah, okay, so why from the top? Why are you saying from the top?
It's like on the sides, it's going all the way through, right? So it's still fine, it's continuity, but on the top, it's like that.
Yeah, so think about it this way, right? If we think about concentric, right, it's building straight the vertical walls, right? So it's giving it more side support if you want to switch it from the side. Okay, but from the top, right, if we switch it, it's going to bend sideways, right? Those walls are going to bend sideways. We have less vertical support. Okay, the next one, which is really cool, is cross. Okay, this forms crosses. Okay, this one gives it more vertical support, but it has the same problem, right? If you squish it from the top, right, it's going to still have not as much vertical support as it does from the sides. Okay, and then that's why we have cross 3D.
Yeah.
Okay, which gives it flexibility in all directions and support from all directions. This is the side view, 45, so like 45. But yeah, just like yes. So just remember, this one you probably want to use with a flexible filament. It's not going to really change much if you use it with PLA.
Prototyping. I think it's faster. Lightning is faster, but remains as much.
Lightning. So for like really quick prototyping models, it keeps it basically calculates it so we can hold up the top. Okay, but then build the rest. So keep yeah, so like yeah, so you're going to have that single line from the bottom, and then with the top, you
Explain the section again with some question.
yeah. Yeah, okay. So
It feels like.
Would not be able to switch if that changes. If it's safe, that's what.
yeah, okay, so like this, right, we have a space between them
Yeah.
that can be squat.
Push it in like the middle.
Yeah, you can push that in, but then it's connected to the top and the bottom, right? There's two adhesions from the top to the bottom, okay?
Yeah.
Yeah, so that's only goes to push this little bit and then this little bit.
Yeah.
Okay, but what's holding the vertical axis? Like what's holding the vertical?
That's.
No, no, no. The main part.
Yeah, so these act as like vertical. Yeah, so if we switch the vertical to the right, there's nothing holding the vertical to the side of each other. So if we put this right and put it sideways, it's that's a bad example. Yes, like the whole.
Nothing line of filament like this.
So this one to this one, okay, it breaks it here, right? It stops it from bending any further here, and with this one then. So if we think about it vertically, you can bend the whole thing there. Because there's no attachment to the side.
Yeah.
I feel like this.
So this goes upwards, okay, you can bend,
Yeah.
you can compress all the way. Okay. It's going to have a horizontal.
Yeah.
Like if you put it sideways, right, then it has like more.
When I thought,
Yeah. That's because okay, we're not doing that.
stop.
Like you do get vertical support, you get it wrong. But you don't get it.
Oh my god, that was like 2 months. Oh, that was so funny.
Okay, the next little setting that we're going to talk about now is travel. So travel can fix a lot of issues, okay? So it can prevent stringing, okay? So that's that little thing between when we're trying to build two bridges, okay? And there's a little bit of filament that's still being extruded out and it creates that string, okay? We don't actually want that there, that's not in the model, okay? But it's just a little attachment that remains. Okay, the two ways that we can fix it is through retraction and something called Z-hop. So retraction should always be enabled, okay? But what it does is the extruder motor pulls back the filament, okay? And it prevents the filament from leaking out, okay? We will look at that little picture there, that's an example there. So it pulls it back out and then it moves and then it pushes it back through when it wants to extrude. The next thing is called Z-hop, okay? It's pretty self-explanatory, okay? So whilst I'm moving the extruder, okay, the Z-axis will move up and then back down, okay? This prevents a string from falling as well, okay? So that's a nice little diagram there. Instead of going from left straight to right, it goes up and then left and then back down, okay? Prevents that string. Z-hop, it's dependent on your model, okay? So if you have a really if you're building two multiple parts pretty separate from each other, you're gonna want to turn on Z-hop just to stop that string happening. But if they're pretty close by and it's one part, I wouldn't worry about it too much. Okay, so in terms of supports, I think a lot of people have seen this. We have two types, right? And then we have a couple of settings as well. So that support structure is either normal or tree, okay? And we have support placement, and then we have support overhang kind of settings, okay? So it's a scaffolding that helps overhangs and bridges from sagging and causing deformation, okay? As we talked about before, okay? So we have two options. We have tree versus normal, okay? And here are the main benefits, really. Okay, tree is computer generated, okay? It calculates what's the best thing. It causes, like a tree, makes branches, okay? To help support it, okay? Whereas normal is pretty old, okay? It was first existed before tree came out. And it's just a rectangular pattern, okay, that goes up, okay, it uses more material and takes longer, okay, and it has more attachments. So in terms of post-processing, a normal structure would be a lot harder to do as well. Okay, so a lot of people, well, I mean, usually everyone uses tree. There's not many use cases you would think you would use normal. I can't really think of any actually. Okay, and then we think about the support overhang angle, okay? So like I said before, it's usually 45 to 60 degrees, okay? However, we have a lot of factors to consider, okay? So what type of printer we're using? We're using Prusa's. These are $1,000 machines, even though half of it's 3D printed. They're $1,000, right? But they can print really well, okay? So we can probably adjust to probably 60, 65 maybe. We can print at that angle there, okay? Print speed, okay? If we go a slower speed, right? Okay, that means the material will cool down quicker, okay? That means that we don't need as, we can have a sharper overhang, okay? We print at a slower speed. The material we're using, okay? So if we're using PETG, it has good adhesion, okay? But it's also at a higher temperature, okay? So we have to consider that, okay? PLA, okay, it's at a lower temperature, it can go down to 190. It won't cause as much, you won't need as much overhang angle, okay? And then the temperature plus cooling, okay? Like I said, PLA can go from 210 all the way to 190, okay? If we're printing at 210, okay, then we have to think about the overhang. Okay, it's gonna melt quicker, okay? It's gonna cool down slower, so we're gonna have a much more overhang, okay? And then cooling, okay? So in the 3D printers, the Prusa's, right? You see that side fan that came down onto the part, okay? Some printers won't have that, okay? So the Mark 4s I know do, I'm not too sure about the Mark 3s. Yeah, but if you have that cooling fan on the side, okay, that can cool your part down, okay? So you can have a much steeper angle. So it's all very dependent. Okay, so support placement, okay? So you have two options, touching the build plate or everywhere, okay? So touching the build plate kind of makes sense in the name, only supports that touch the build plate, okay? So it takes more time and material, but it leads to more easier post-processing, okay? So that's because it's not creating joints from one part of the model to another part. You're not building onto the model and then building onto it again to support it, okay? Whereas if we choose everywhere, okay, that's what would happen, right? It would create supports from, say, the bottom of the model, okay, to the top of it, and then you have to clean up what the parts are. Okay, and so the only case where we use everywhere is if we have a really highly complex model, okay? And you can't, and that would create less sag in a cleaner model, excluding the post-processing. Okay, so here's an example for this one, okay? So if we used everywhere, okay, that's what would happen. Okay, it would take 11 hours, 57 minutes, okay? Use 27 meters, okay? And that would be an absolute pain to clean up, okay? Touching the build plate, much better, right? Okay, so we only have this switch, it takes 10 hours to 7 minutes, okay? But then if we try treat, okay, takes a bit longer, right? But you have so much less bits touching it. So you see the supports there, okay? It's all calculated and it's only touching the bits that need to. So it's very, very accurate. I mean, it's very good for building support. Okay, so now onto our troubleshooting steps. We talked a bit about them during the induction, but I'll go through them. So poor or no adherence, I think that's our biggest one here, okay? Like you said before, if it doesn't, like 90%, like if your build adheres at the start, it's going to be fine, basically. If not, it's going to decache. And this is an example here. This is the spaghetti he was talking about when it doesn't adhere. Okay, so that's one, it was two parts. So that's one part, and then the other part detached and then just did that. Okay, so these are the reasons, right? So we can have a dirty print bed, okay? We due to high print speed. It could be due to bad print bed calibration. It could be due to a small model, okay? Or it can be due to extruder or print bed temperature as well. Okay, so with the dirty print bed, we have filament residue, debris and oils that can remain on the print bed and stop the adhesion. Pretty simple fix, clean it basically. So we want to remove the old filament, okay? For PLA, we want to use isopropyl alcohol to clean it, okay? So you'll see next to the 3D printers as bottles of isopropyl alcohol. You use and paper towel, you just wipe it off. Or you can use acetone for ABS, okay? But not many people use ABS anymore, so it's usually not isopropyl. The next one, print speed, okay? So I don't know what the Prusa's are pretty quick machines, but usually I would say 80 to 100 is what you'll be aiming for, okay? Especially if it's a really intricate model and has very low adhesion at the start, okay? Because it won't allow the filament to bond to the build plate, and might remove the already previously printed filament, okay? So the three settings that we want to change is print speed, okay? So anywhere from 80 to 100, I think is fine. I'm not too sure, 120 for process, I would say 80 to 120 would be fine, okay? But the main ones that we're looking at here is that initial layer speed and the skirt and brim speed. Okay, so we can set that down to slower speed just to get us started and get that initial layer adhered. Okay, and the next one is the print bed calibration. So we all did this before. Okay, so it calibrates all the axes. Okay, ensures good adhesion. Okay, some of the issues that can happen is a broken or detached sensor. Okay, and a Z offset. So what do I mean by broken or detached sensor? Here we have an example, hopefully. So either the X, Y, or Z sensors are broken or disconnected, and the stepper motor will continue to run because there's nothing telling it to stop, right? Because the limit switches aren't there. And nope. Can you click that video? Sorry.
Thing to home its axis. I had to turn the printer off fast.
When it's not hitting that limit switch. Okay, but with this is not so much for the Prusa's, because the Prusa's are very smart and they don't have these limit switches anymore. Okay, so they don't have the limit switches they do on the right and left. They actually can sense when that motor is whirring, and doing that it keeps on going and it stops itself. But the one sensor it does have that hinder sensor for the Z axis, and that can break, and then that extruder head will just keep going down potentially sometimes. Okay, so the next thing is that Z offset. So here's an explanation of the Z offset. So Z offset is the distance from the sensor, okay, the Z sensor to the extruder head, okay. And we know that sometimes it's not correct, like we had in that group over there. It was like 2 mil above it, so you have to bring it down sometimes, okay. And a good rule of thumb that I used to learn from when we didn't have the sensors and you have to manually do it, is that you should have a sheet of paper that can slide underneath it. That's a good layout. Okay, so just imagine that. And then here's an example. Okay, so we have too high, perfect, and too low. Okay, and so the Z offset can be accidentally altered in moving the printer, changing the build plate, or just maintenance itself. Okay, so you want it in that perfect zone. Okay, and then here, that light adjusted like we talked about. Okay, so small model, right? Models with small contact area with build plate will tend to detach at the start or middle of the print. Okay, the things that we can do to fix this, okay, is use a brim, okay, or increase the layer of existing brim. Okay, so if we try to brim right and it's not adhering still, okay, we can either increase the layer count or we can change it to a raft, which is a bit excessive, I would say. So just brim and then keep adding layers if it's not adhering. Okay. The other thing we can do is reorientate that model. Okay. So there's a larger contact area between the build plate and the model. Okay. So for that example there, just flip it. Okay. We can flip it. Got a much bigger build plate area, or if we were not thinking, we can add a little brim to it to try again. Okay, the main one here is build plate temperature, right? So sometimes build plate temperature is too low, okay, and you won't get that glassing stage, okay. So PLA or most materials have a glassing temperature, where it's like sort of liquid, sort of not, sort of solid, sort of liquid, and then that's the temperature we want when it wants to stick to the build plate. Okay, so if it's too low, the initial layers will contract, okay, too quickly and not adhere. Okay, and this will cause warping. But at the same time, if it's too high of a temperature, okay, it will step outside this glass zone, okay, and will allow the filament to cool and adhere. Will not allow it to cool and adhere, okay, and this will cause warping as well. Okay, so for both scenarios, we change to the temperature in 5-degree increments. Okay. Okay, so filament issues is the last little bit. Okay, so when we want to change filament, okay, there's a little video here, but the main thing I want you guys
On the control
here is to cut the filament at a 45-degree angle in the video. Okay.
Press the knob to access the menu. Scroll down and select Unload Filament. Then select the filament material that is currently loaded in the printer. The printer's nozzle will begin heating up to the preset temperature. This will take about a minute.
DNV, they will.
Once it is close to the preset temperature, the control panel will prompt you to press the knob to unload the filament. The printer head will move upwards while withdrawing the filament. Let it stop before you pull out the filament. Then you can remove the filament spool. Before you insert the new filament, cut the filament tip at a 45-degree angle. This will allow you to smoothly feed the filament into the print head. If you do not cut the tip, it might get stuck in the print head during insertion. On the control panel, go to the main menu, scroll down and select Load Filament. If the nozzle temperature is already heated up to the preset temperature and filament auto-load is active, the screen will remain unchanged. You can press the knob again to confirm it. The printer's settings must be changed to use other materials or brands besides the Prusament PLA. Now we insert the new filament. Place the spool onto the holder and feed the filament into the print head. The print head will automatically rise up as you feed it. This provides clearance for filament extrusion at the nozzle so as to clear the print head of any previous filament. Ensure the nozzle is not jammed or clogged.
Yeah, so that's all done. It'll be easier trying to explain. Okay, the next one is a clogged nozzle. Okay, so when we have bad filament, okay, or it's breed gets stuck in that end of the nozzle. Okay, so it's trying to extrude a 1.75 mil filament out of a 0.4 millimeter hole, basically. Okay, so it can cause a partial or complete block, and this is what sometimes your part might look like. Okay, and usually at DNV, right, just what you guys be used to, just ask on the guys to fix it. but the three methods to fix this is either to change the filament, so pull it out, okay, force the filament, so this is when you heat it up really hot, and then just literally turn off the motor and just push the filament through until you see a clog, or a cold pull, which is the most common method. Okay, and then the next video is what example of cold pull would look like. And this guy has cut his extrusion head out in half, so you can see it. But yeah, so a cold pull is where you heat it up, push the filament through, and then let it cool down, and then you yank it out whilst it's still cooling down. So it pulls out anything stuck to it. And hopefully it shows you the stuff. Yeah. Yeah. And yeah, that was it. Any issues that you run into will usually be first layer adhesion. Okay, and if it's not happening there, think about height, think about temperature. Okay, and that's basically it. And the plate.
Okay.